Hello, everyone, and welcome to today's AI Agent Frontier seminar. I am Mingjin from Virginia Tech. Today, we are really thrilled to have Dr. Akshara Rai from Meta AI. Akshara is a leading expert in embodied intelligence and sample-efficient robot learning. And today, her talk will be about simulation to real transfer for home robots. Just a reminder for today's seminar, we'll have about 40 to 45 minutes of the presentation, and there will be a dedicated Q&A sessions towards the end. Let's give Dr. Rai a warm welcome. And Dr. Rai, the floor is yours.
Thank you so much for the nice introduction, Ming. It's great to be here. Hi, everybody. I'm Akshara. Today, I'll talk to you about some work on Sim2Real learning for home robots. So let me first tell you a bit about myself. As Ming already said, I'm Akshara. I'm a research scientist at FAIR at Meta. I'm located in California. My research focuses on sample efficient learning for robots using different approaches like Sim2Real, prior knowledge, and some elements of optimal control. Today, I will focus largely on Sim2Real as well as introduce some in owned work, which was combining Sim2Real with some optimal control. Before this, I did my PhD from Carnegie Mellon University in Pittsburgh, where my thesis was on Sim2Real for bipedal locomotion. So yeah, what are we trying to do at FAIR robotics in general, and my research in general kind of aims to have this an autonomous home robot which can operate in homes. This is like an unseen house, let's say, for the robot. It has been tasked with cleaning up the house, and it's not alone. The important bit is that the robot is not alone in the house. There are other people in the house. And now the robot has to achieve this long horizon task that it was prescribed while taking other agents like humans into account. So it has to basically not only be really good at long horizon, useful everyday tasks, but it also has to take into account things like safety and collaboration. So if the human is mopping the floor, the robot takes over moving bowls and cups from the living room to the kitchen, for example. So how can we get this kind of autonomy and especially safe autonomy in the home? And there's many different like aspects to this problem. It's a very wide range problem. I will talk about a few aspects that I have worked on. So such coexistence of human and robot in the same environment has some requirements. One thing very obviously is that the robot has to be highly skilled at long horizon everyday tasks. So if the robot cannot do everyday tasks, there's no use in it being safe, right? So we do want robots to be capable. So here is a work that we did in which, for example, a spot robot was asked to clean up the house, and it's exploring the house, finding objects that are out of place and like putting them in some prescribed locations. So the toy cars, it's moving to cabinets, soft toys to hampers, and so on. And this is kind of an image of what future robots might be like. But the robot will not operate in the home alone, so it has to be reactive and responsive to changes in the environment. So let's say there's a person in the environment, like here I am walking in front of the robot. The robot has to take this into account, that there's a human in the environment, and then react to this change and then like avoid as it tries to complete its task. Finally, it would be ideal if the robot is actually able to communicate with the humans, so it's able to follow natural language commands as well as collaborate. So here, for example, the task is let's clean up the bedroom, and the human and the robot collaborate at the task of cleaning up the room. And the robot is basically not dependent on the human to do the task, but it is aware of the human. So the actions it does is aware of what actions human is taking to make sure that the human is safe, as well as collaborate efficiently with them. So it's not repeating things that the human has already done, for example. So I will present three works today, which address three different aspects, these three aspects that I just mentioned. And the goal is that this hopefully inspires some of you to work on such challenging problems, as well as like add even more interesting safety guarantees and such in the future. So, sorry. The first problem that I mentioned was, how do we build capable robots, right? So how do we teach robots to do long horizon tasks? And in this work that we did about 3 years ago, we were trying to see if we can use simulations to teach robots complex tasks. So at the time, basically, we had this habitat simulation showed on the right, which is very photorealistic. It has very diverse sets of environments and scenes, and it's fast to render. So given this kind of a simulator, and we started using the Boston Dynamics spot robot shown on the left here. So given this kind of a spot robot, which has somewhat mature functionalities and a very diverse simulation, can we teach robots to basically do indoor tasks like tidying up and then deploy this in the real world? So we built this approach called adaptive skill coordination, where we essentially broke down the problem into first learning some basic skills, navigation, grasping, and placing, followed by learning a coordination and corrective policy. And the idea here was that first the robot learns to do individual skills in isolation, and then we learn a policy that decides which skill to call when, depending on a long horizon task. And finally, a corrective policy was used to adapt the actions produced by our learned skills in the real world for better Sim2Real transfer. So let's look into this a bit more in detail. So the step one, as I said, was learning some basic skills for the robot. So we learned a navigation skill where the robot basically just learns to move its body without interacting with the environment. A grasping skill in which, given some initial position, the robot learns to move its arm so that it can grasp the object. And then a placing skill where, again, the robot is already located close to a placing location or a receptacle, and now it needs to place an object on this placing location. So it just learns to move its arm. So the idea was that the navigation skill was moving the base mostly, and the grasp and place skill were mostly moving the arm, and combining all three of them would result in long horizon navigate, pick, navigate, place tasks. Let's look a bit more into detail into how each of these skills was learned. So this is the navigation skill. On the left, you see our simulation environment habitat that I talked about with a spot initialized in it. On the right, you see what are the observations that the robot is getting. So the robot gets 2 depth observations from its 2 front cameras, and these cameras are slightly tilted. That's why the depth observations look a bit funny. But there's 2 front depth cameras that the robot is getting observations from here. And then the action that the robot is commanding is its base velocities. So if you notice that the legs of the robot are not moving in this simulation. And this is because what we command is not leg motion or forces. We command forward and rotational velocity of the center of mass. And then in the real world, since we are using a Boston Dynamics spot robot, Boston Dynamics provides a really good API for controlling the base velocity of the robot. So we basically learn a policy that can operate in an abstraction that we know our hardware is mature enough to follow well. So here, for example, this is an unseen environment for the robot. It's purely using its onboard sensing to explore this environment and then following nearly optimal paths in basically empirically to achieve a target position. And this is a really powerful framework because now we can take this robot and place it in any house that we want and give it a target location, and it should be able to navigate this new house. Now, we don't need to pre-map the house. We don't need to simulate the house, do none of those things. Similarly, we try to train a grasping skill, which is able to grasp arbitrary objects. So we initialize these cluttered environments in simulation, and then the robot has to move its arm so that it can pick up a particular object. Now, again, notice that we are not simulating the low-level grasping dynamics because, again, here we were depending on the Boston Dynamics grasping API. So Boston Dynamics Spot comes with a grasping API, which doesn't work in a lot of situations. But if you have the hand centered on top of the object and close to the object, it works reasonably well. So that's what we tried to do here, is that instead of trying to simulate very complex grasping physics and then transfer them Sim2Real, we tried to utilize real-world controllers from Boston Dynamics to move the where we learn to move the arm very close to the object and then call this grasping API. So on the right again are the sensory observations that the robot is getting, and the robot does not get RGB. The first observation is depth. It's getting depth from a camera located on its gripper. And then the other observation it's getting is a bounding box. So instead of getting pure RGB, what we do is we draw a bounding box around our target object, and the robot uses this bounding box image as a signal to center itself on the target object. And this allows it to basically move its arms so that it can orient itself towards the target object, even in cluttered environments. And similarly, for placing, we don't, again, simulate complex placing dynamics, but instead move the arm and then open a gripper, for example, in the real world, and place the object on a target location. So again, this is almost a reaching task where the robot is trying to avoid the obstacles in the environment, such as the table. So find a path which is able to avoid table and cabinets, but then reach a target location and then drop the object there. So once we have trained these three skills, the next task at hand is to actually do coordination. So now we have learned navigation, grasping, and placing, and now we need to sequence them in some ways so that we can successfully achieve the task of pick up a cup and bring it to the dining table. And that's where the coordination skill comes. This is a mixture of expert skill, which decides whether to turn on the navigation skill, whether to turn on the grasping or placing skill. And then finally, we need a corrective skill because there is a distribution mismatch between simulation and real world, but also within simulation in the skills. So the skills are trained on individual tasks, but now they are being deployed on a completely new task, right? So they were trained on navigation, grasping, and placing, but they're being deployed on pick and place of arbitrary objects. And that's why we need a corrective component to correct for these slight out of distribution situations that might arise in the end-to-end task. And together, we are commanding forward velocity, angular velocity of the base, as well as joint displacements for the arm. So here is basically the whole how the learning works for corrective and coordinating policies. So we basically initialize a lot of these pick and place environments, and the coordinating policy chooses which skill should be called when, and the corrective policy adds small corrections to the actions commanded by the individual skills to improve overall performance. And then now that this system is trained, we can actually deploy zero shot in this completely unseen environment. So this apartment is a test apartment we have in our facility. This was not in the simulated scenes that the robot was trained on. These objects are not in the objects that the robot was trained on. So the scene, the object, the layout, everything is unseen to the robot. But it does know that the clutter, it knows which objects are clutter and which are not. So it knows the car, the ball, the soft toys are clutter objects that it needs to clear out and where to place them. So what it's doing is that it's starting from its home position. It's navigating to different receptacles in the house, different rooms in the house. It explores using its onboard cameras. It finds objects out of place. It picks up those objects and it takes them to their target location. And this is done with basically no data from this environment or these specific objects. Since we don't use any environment-specific data, we can also deploy this in the wild. But here it is in a Georgia Tech lab. Again, this environment is not in the training environment, and the robot is able to do the same task here. And I don't have videos, but we actually took it outside. Oh, actually, might have a video in a bit. But yeah, we also took it to like other environments. Now, the other bit about this policy is that since it's not taking the map of the environment, it's actually very robust to moving obstacles and people. So it's, I move around this curtain, which is like almost a moving wall, and the robot is still able to reach its target location, which is the ball. So it's first trying to go around here. Since I blocked the path, it replans and tries to go around the kitchen island. But now, since that is blocked, it actually goes back to where it was going before and is able to reach its target location. Similarly, yeah, I already showed this video, but here I am standing in front of the robot, and it's able to basically avoid me to go and goes around me to go to its target location. And this is basically a powerful paradigm because not only is it robust to environment changes, it's also robust to moving obstacles and people. And this is another task. So actually, it turns out I don't have videos of other places, but yeah, we took it outside. We took it to a lot of places, and it was still able to perform this task. But now we can even add an LLM to the mix. Like so far, I was specifying the task and like, here are the objects, move these objects to some other location. But by adding like large language models, adding some object detectors, which are more, generic open set, I can do arbitrary things like bring chocolate boxes, cereal box, and pill bottle from the kitchen to the bedroom table. So here, Spot is just taking this language instruction and doing this task. So, but again, in all of these settings, the robot is in isolation. So we are able to build functional robots using using this approach, but they are not capable of operating around humans. So how do we study how to operate around humans? For this purpose, we built the next version of Habitat Simulator, which is Habitat 3.0, where we added people to the simulation explicitly. So now the robot is not just learning how to do a long horizon task, it's learning how to do this with people in the mix. And now we can basically do a very similar approach to what I just described of like training policies in simulation and then deploying them to the real world. But now we have people in the mix. So what this lets us do is some really nifty things. Like here we define a task of finding and following a human. So the robot is initialized in an unseen environment. So this house, this massive house is unseen to the robot. Robot is initialized in some random location. The human is initialized in some random location. And the robot is looking for the human. And then once it finds the human, it's going to follow the human, but maintain a safety distance. So this is a pretty simple task definition, and we just use reinforcement learning to train a navigation policy. But there's some really interesting social cues that come out here. So the human turns around, and the robot immediately starts backing up to not block the human's path and let the human go by. And now it's following the human at a safe distance that we have defined. Now the human turns around again, and again, see how the robot backs up a very long distance to move out of the way of the human and let them pass. And we call this task social navigation. And this is basically a really beautiful, to me at least, a very beautiful result in which like the robot is very naturally basically giving way to the human in this, in how two humans would interact in space. And the reason we can learn these kind of policies without like excessive, teleoperation or even real people data collection is because we have added a human into the simulator, and now we can just simulate policies and learn policies that act around humans. So we take now that we could do basically navigation around people, we also wanted to study now collaboration, right? So sure, you can find and follow people, it's really cool, but what if we actually wanted to work together with people? And this is kind of like, I think the holy grail in the way of human robot interaction is how do we benchmark how well a robot is doing in the presence of people? And for this, we built this extensive benchmark called Partner, which is designed in the Habitat 3.0 simulator I talked about, and basically tries to measure how efficient are robot assistants at collaborating with people on everyday tasks. So we define a very large number of tasks which have some different characteristics. So for example, The tasks can be constraint free. So the task could be, let's move all dirty plates to the sink. They can have some spatial constraints. For example, place the books next to each other. They can have temporal components like let's move the candles out before we place plates on the table, as well as they can have some heterogeneous components. So let's say that the robot cannot wash dishes, but the human can wash dishes. If the task is let's wash the dishes, then the robot should still bring dishes to the human, but let the human do the washing. So this kind of reasoning that the other agent is more capable than I am, but how can I still assist them, is something that we would want future robot assistants to have. And Partner basically incorporates these kind of tasks. Um, so in the past video that I showed, the human was just a random walker, but now actually what we want to do is model the human doing some part of the task. So the human can choose to just give an instruction and sit, which is totally fine. But the human might also actually do some part of the task. And what we want the robot to now understand is how should I assist a human given what they're doing? And this brings like interesting components about theory of mind and optimal task distribution and so on. But to do this, we need to model humans in the simulator. So what we did was we had two ways of modeling humans. The first was actually use another language model, which is prompted with like a personality of the human and a task description to simulate the human. But but an even better way is actually put the human in the environment and then let a human control the human. So basically, we have an avatar in the simulator. We make a Unity-based framework where an actual human can now control this avatar. And now the robot is actually collaborating in simulation with a real human. It's just the real human is controlling an avatar. And what this lets us do is actually add humans to the reward function. So far we've been doing reinforcement learning, and a lot of people even now do reinforcement learning with robots operating in a vacuum. So basically, there's a very clean environment that the robot is operating in, and you're trying to learn objectives. You design objectives for this environment. But now with this simulator, we can add actual humans to the reward function, which means that now we can learn things with humans in the loop. And with this benchmark, we released this earlier this year, this benchmark and this paper. It was at ICLR, presented at ICLR this year. What we can now study is how well our state-of-the-art planning approaches at multi-agent tasks. And I mean, no surprises there. They are pretty bad. Even if they succeed at the task, even if the success rate is high for some of these approaches, their efficiency is really low. So they're like taking as much time as a single agent, sometimes more time than a single agent to complete the task. And this is because they're basically redoing what the human already did, or getting in the way of each other, undoing things often that the human already did. So really, really not optimized. But then an even worse part is that because LLMs have no reasoning, physical reasoning, right? Like they don't actually understand, they're not taking visual inputs, for example, to decide what to do. They're taking some language-based representation of the world. They are unable to avoid any collision. So all of these approaches that we tested had very high number of collisions between human and robot. This was despite the fact that we learned policies that I was showing before, which should avoid collisions. But the trouble is that if your high-level planner is asking the robot to continually go to the same location that the human is at, you can't avoid collisions after a while. So clearly there was a lot, we basically discovered that there's a lot of room for improvement in human-robot interaction before we can put out these controllers, these policies out in the world with actual humans. So this brings me to basically the safety component of this talk. And this is a pretty old work that I will describe a bit. But I hope that together with the previous parts of this talk, it is at least inspiring to people on pursuing basically safety for human-robot interactions in some ways. So as I said, when we test these policies with humans in the loop, even in simulation, we see that they are colliding with humans a lot. So the question basically arises, how do we ensure safety of learned policies, right? And this is a very open-ended question, very challenging question. I don't have an answer. But I can talk about this prior work that we did, which tried to add some safety into reinforcement learning. So what we used here was a least restrictive safety controller. And the basic idea in this controller is that if in your current state you're safe, you should apply any action that you want. But if your current state is unsafe, then apply actions from a learned safety policy. So basically, a safety policy is a policy that will take you away from your unsafe states, bring you back into a safe state, and then apply that action when we are close to unsafety, but otherwise close to danger, but otherwise just apply any action that you have learned from your policy. Now, the obvious question here is, what is unsafe or an unsafe state? How do you define these states, and how do you learn the safety policy? So to define safe versus unsafe states, we use the Hamilton-Jacobi reachability formulation. And the Hamilton-Jacobi reachability is essentially trying to model the states from which a system can avoid the danger zone or unsafe states given any disturbance. So given the, in this picture on the right, dark gray is the unsafe zone. So this is the zone that we should not enter. And the light gray, sorry, light gray represents a set of states from which, in the worst case disturbance, you could not avoid going to the target or unsafe state or the danger zone. Sorry. So how does Hamilton-Jacobi reachability do this? So the goal here basically is to stay in the white zone, which is the controllably safe states, which means that in these states we have an action that will keep us from entering the dark gray zone. The light gray zone is already unsafe because we cannot guarantee that we will not enter the danger zone in the light gray areas. Again, so remember, this doesn't mean that if I'm in the light gray zone, I will enter the dark gray, right? It just means under worst case disturbance, I would not be able to guarantee that that I don't hit the dark gray zone. And this is a very conservative measure, but this is basically backward reachability to ensure guaranteed safety. So the way that reachability, Hamilton-Jacobi reachability formulates this is through a value function that measures the closest a trajectory from any state reaches this danger zone in dark gray, given the best possible control. So with the best possible controller, in this case, learned using dynamic programming, what are the states that will not reach the unsafe zone? And then the safe set is defined as states for which v of x is greater than 0. Now, typically you want some margin because you don't just want v of x equal to 0. So we define some epsilon parameter that which is a hyperparameter that we tune for our task. And now what this means is that in the safe set X, there's always an action that will keep you from entering your danger zone, even under worst case disturbance. But as I said, this Hamilton-Jacobi reachability is calculated using dynamic programming, which famously doesn't scale for higher dimensions. So in 2019, there was a work from Claire Tomlin's group, which tried to bridge the gap between reachability and reinforcement learning. So this value function v of x that was being used to calculate safety can also serve as a safety critic. And then now you can use it as in an actor-critic framework to learn a policy pi of x, which is the safety policy, using a standard reinforcement learning algorithm like soft actor critic. So what this means is that now we can approximate both v of x and pi of x as neural networks. And this allows us to generalize reachability to much higher dimensional problems. So for example, on the right is a very simple example of a Dubin's car. So the red zone is the obstacle, danger zone. The green is the target that the car is trying to reach. And what's shown in black here is the states from which there isn't a guaranteed controller anymore. So this is the light gray from the last picture, this is the dark gray, and green is the target. So what you'll see is that as this blob moves, it not only avoids the red, it also avoids the black, so that it can, it doesn't, in the under worst case disturbance, it's not hitting the goal here. So this was pretty promising because now you could do Hamilton-Jacobi reachability for high dimension systems, but it was still assuming a perfect dynamics model of the world. And a perfect dynamics model of the world is kind of a strong assumption for robots that are operating in houses, because imagine every time you lift an object, like a cup, now your dynamics has changed because now you're lifting a heavy weight, right? So if all my safety guarantees were designed for an empty manipulator operating in space, and now I have to lift an object because that's what manipulators are for, and my guarantees are not valid anymore, then they are not very useful, right? So what we need to do is build guarantees that are able to operate under uncertainty. And in this work, we explicitly considered uncertainty in dynamics. And the idea was that every time you pick up an object with a manipulator or with a quadrotor, your dynamics, your especially inertial and weight parameters are going to change. So how can you accommodate for that in in Hamilton-Jacobi reachability? So we defined a two-step learning process here, in which in step one, we basically learn a conservative safety policy offline for a wide range of dynamics. And here, basically what we do is that we say that our dynamics is drawn from a distribution P. And when we learn the safe policy, learn it so that it can generalize to all the dynamics in this distribution P by conditioning it on a specific P. So it considers basically empty arm as well as a heavy object, as well as a light object, and all combinations of objects. So you make a very broad distribution of what kind of objects this arm can pick up. And then you learn a policy which is conditioned on each of these objects, for example. Now at test time, this might be too conservative, right? Because the object I'm lifting is probably very light from the object that, which was the heaviest object in P. So at test time in online, not only do you calculate your safety with respect to all the parameters in your distribution, but you also update your mass distribution at test time. So what we basically do is that at initial state X, we roll out policies to a time horizon of T and look at how many of these basically stay in the safe set. And if all of these stay in the safe set, then we say that this is a safe state. So let's apply our task policy here. If even one of these trajectories enters an unsafe set, this state is determined as unsafe, and now we apply our safety policy using the best estimate of our dynamics. Once we apply this action, we basically get a data point of our new dynamics, and then we update our dynamics. So now P that was used in offline calculations is updated online, so that we have basically our distribution shrinks more and more towards the true distribution of dynamics. And then eventually, basically, if if it's a linear system and under a lot of assumptions, basically we are guaranteed to reach the true dynamic state while staying safe the whole time. So how this plays out, for example, this is a 2D link manipulator, and there's uncertainty in the mass of the final link. So an initial estimate of the mass is 1.9, and there's a distribution, a Gaussian distribution around this mass. Red is the danger zone that it should avoid, and green is the target that it's supposed to reach. And notice that we are starting it with a high velocity going towards this obstacle, red. So when we apply it like this, we see this kind of behavior. So initially we were applying the task policy, but then we apply the safety policy, and it results in this push-pull behavior a bit, that the safety policy pushes it away, the task policy might take it close again, the safety policy pushes it away again, and eventually basically the policy brings it back to the target goal without hitting the obstacle. Now, if you look at the top again, what you see is that as it's doing this, it's also updating its mass. So it started with 1.9 as the mass estimate, and then as it gets new parameters from the environment, it updates its mass as well as its uncertainty over the mass, and then eventually converges to the correct mass of the system, which is 2.0, and no uncertainty over this mass. And this means that now the policy is basically not overly conservative. It's safe for the system that we have at hand. And we basically tested this approach against any updates. And with our framework, where we added updates to the mass and value function, and we saw basically that it avoids these obstacles more often. Now, in the past experiment, you saw that there was this conflict, right? Like basically there was a task policy that was trying to move the arm towards the obstacle, and because it didn't know about the obstacle. And there was a safety policy that was pushing it away. So there was this somewhat suboptimal behavior. So what we did in this second portion of this work was actually combine the safety policy with model-based reinforcement learning. So what model-based reinforcement learning tries to do is that it tries to optimize an action sequence for a horizon H for some cost function C, given that there's a dynamics model of the system, and this is again a learned dynamics model. And what we add is a safe set constraint. So not only are we optimizing the cost function given a dynamics model, but we are also making sure that we don't enter unsafe states as we do this optimization as best as we can. So there's two horizons here. One horizon is the planning horizon, and one horizon is the safety horizon. So these are two different hyperparameters. H is the planning horizon, and T is the safety horizon. And typically the safety horizon will be much longer than the planning horizon. And we deploy the system on like a bunch of different manipulators, as well as a quadrotor of different dimensions. And then we like add different types of noises. And we study basically some random initializations. And these random initializations around 0, for example, have pretty high success rate. But then we even created some very challenging scenarios in which basically we initialize the robot very close to the danger zone, and then like moving towards the danger zone. And then because in the end, everything is learned with reinforcement learning. The value function is learned with reinforcement learning. The safety policy is learned with reinforcement learning. For very high uncertainty and very large, very challenging positions, we actually can't guarantee that we will avoid the danger zone, but still we end up getting much higher rate of success than policy which does not do these updates. So this basically gives us a somewhat a general formula on how to combine reinforcement learning with safety. So one way of doing it is that we build capable skills in simulation. And this is kind of the first half of my talk was how do we build, teach robots to do things like navigation, grasping, placing, and these work, deploy them in the real world. And then we can benchmark these with humans in the loop, right? So clearly, even before we deploy it in the real world, we want these policies to be able to work with humans in the loop and basically be safe around humans in simulation. And then once we are happy that, oh, they have more than like, 90% success without hitting any humans, then what we can do is we can actually deploy them in real world scenarios with actual humans. but with safety wrappers. So this least restrictive safety controller that I talked about is kind of a safety wrapper, which hopefully lets your policy act how it was trained in most scenarios, except when when a state is deemed unsafe, and then it basically moves your system away from this unsafe state. But there are many, many challenges in this approach. There's basically very tough compromises that we have to make in terms of problem complexity, safety, and planning horizon. So when I'm just doing reinforcement learning, I can do reinforcement learning from these visual inputs that are operating in these large homes. On the other hand, when I do safety analysis, I'm working on these planar manipulator arms. So how do we, I think it's a open question of how do we actually apply these Hamilton-Jacobi reachability or similar approaches to very high dimensional systems that are operating on visual input and keep some of these safety measures, safety guarantees. I mean, we already lose a lot of these safety guarantees when we start using reinforcement learning, but at least, it's still higher performance, fewer collisions than not using these approaches. And the next question is basically, how do we model complex dynamics like contacts, right? So a robot which is operating in the house has to pick up objects, it has to open doors. It's unclear how to take, first of all, like it's very challenging to model these contacts. They are very high dimensional and notoriously tough to transfer Sim2Real. But how to do safety analysis on them is like completely unknown. And I think an interesting approach out there, I think, is to basically use learn simulators or even world models to actually approximate these contact models and then do analysis on these models. I think a natural question is that a lot of these approaches are thinking about worst case disturbance, but most realistically, the disturbance you see won't be worst case. So is it too conservative to do worst case, or is it a requirement to guarantee safety? So this is clearly problem dependent, and I think it's a trade-off that one has to make, and it would be good to build systems where you can basically tune your risk as your problem determines. And then I think lastly, it's this world of safe RL is still somewhat detached from like modern multimodal models like VLMs and LLMs. And what we see is that these models are really good at semantic knowledge, right? So they don't need Hamilton-Jacobi reachability to tell them that if I'm next to a wall and I shouldn't hit a wall, then I should just move away from it, right? So how do we combine the priors from VLMs, LLMs in these approaches so that we can basically jumpstart safety much more efficiently? But yeah, that was my talk. Thank you, and I'm happy to answer any questions.
Yeah, thank you, Dr. Rai. That was fantastic. And let's open the floor for questions. And please feel free to raise your hands or put your questions in the chat. Be happy to read it for you. Actually, let me jump start with a question from my own. I want to ask about the part on skill learning. So you mentioned that you are teaching the robots a set of primitive skills like navigation, placing, or grasping. And I like to think of them as a toolbox. So how do you how do you actually teach the robots to learn these skills independently so they don't bleed into each other's? And how do you make sure that they know what skill to pull out at test time?
Yeah, so independently, we teach them each skill by basically defining a reward function per skill in a way. So the action space for the navigation skill was only the base motion. It was not allowed to move the arm. And the goal was to basically reach a target location. The action space for the grasp skill here was only to move the arm. It was not allowed to move the base. And the goal was basically to center on a particular target object. using this bounding box image. For place, again, the action space is to move the arm. So it does have the same action space as the grasp, but the cost function is again to do reaching while avoiding collisions with the environment. So each skill is trained separately with different reward functions. So they're trained completely independently of each other. But the important bit basically comes in how do you sequence them together. And like there's this thing called handoff errors, that my navigation skill might end too far away, and now my grasping has no way of succeeding because the grasping is not allowed to move my base. So how is it ever going to pick up an object if it's too far away, right? So for this reason, we basically learn the coordination and the corrective skills. So the coordination skill is the skill that's trained only to sequence skills. So given the pre-trained navigation, grasp, and place skills, the coordination skill is trained to decide when to turn on the navigation, when to turn on the grasping, and when to turn on the placing. And it can turn on two at a time. So it can decide to basically navigate and grasp at the same time if it thinks this is feasible. But this skill is learned with reinforcement learning. So again, it's trained in simulation with reinforcement learning as well. So it's trained with the idea of achieving long horizon tasks. So it's not going to turn on grasping and placing just because it should result in low performance when we are training the skill. So it doesn't have very large amount of triads. And then finally, we train this corrective skill, which has basically the action space of the whole robot. So this skill can change the base as well as the arm with the intention of taking care of situations like handoff errors. So if my navigation skill ended too far away so that the grasp cannot succeed, the corrective skill can basically move the base forward closer to the object so that it's able to so that the grasp skill is able to grasp the object. So to give you an idea, basically, this is the selected skill as per the coordination policy down here. So that's what's shown in red. So it's going nav, then it selects grasp, then it selects place. But at the same time, there's like corrective motions being added. So even when it's doing grasping or placing, the corrective skill might reorient the base a little bit so that it's closer to the object. Or it might reorient the arm during navigation so that the arm can reach the target location better. And so that's kind of how we, just learn how to sequence the skills and then when to call which one.
Perfect. I think that makes sense. Yeah, so also thinking about the safety aspect you talk later, the safety can be also treated as a skill. So I'm wondering, like, if you treat like safety as a skill, then how do you like balance safety with utility skills that the robots needs for a typical operations?
Yeah, so what we were trying to do was this least restrictive approach in which I like the idea that basically you could use a new skill, which is safety, which gets called whenever the coordination, there's basically some other skill which is deciding if it's safe versus unsafe, and then calling the safety skill if it's unsafe, right? And I think what we were thinking of this was this least restrictive framework. So in a way, there's a classifier which is saying, is your value function greater than epsilon or less than epsilon in your current state? And then if it says that it's less than epsilon, then it decides to call the safe skill. Versus if it's more than epsilon, then it continues calling the task skills. And then I think basically the challenge is how to learn this classifier so that it's able to use more general dynamics, not just like simplified dynamics as input. And then what should the safety skill be for these general dynamics as well, right? Because the dynamics also make the safety skill learning much harder. So if they're moving humans in the environment, I mean, we could take the human as a disturbance, and then we are kind of just trying to learn policies which are worst case disturbance. So in a way, like the work in a way, basically, sorry, this skill, the navigation skill that I showed, is in a way trying to do this, that it's whenever the human turns around, it starts backing up away from the human. So it's taking like the current state of the human into account into determining when it should follow the human versus when should it start backing out. But this is actually just one skill, but we could do this in two skills, for example, one skill that is actually just following the human, and the other skill which is backing out if there are, unsafe scenarios detected.
Got it. Yeah, thanks. Yeah, the reason I'm interested is because we also have a similar challenge when training the language models to have different skills, like backtracking an error or reflect on the plan or some other things we want it to learn. So it's really nice to see that it's a shared challenge in the robot learning as well and see your approach.
Thanks.
Okay, great. So actually, let's open up the floor to see the questions from the audience. Okay, so I can read it from here. So Menglu asked, okay, thanks for the promising talk. He asked about what's the corrective part designed during skill coordination correction? Is it aligned designed for the VRM or the LRM? I think you have a talk about the coordination part. Maybe we can focus more on the VRM and LRM part.
Um, so, so the corrective is not doing high-level reasoning as much as it's kind of doing low-level adaptation, if that makes sense. So I would say that okay. So the way I would think about a VLM and LLM is that it's a high-level planner, which is deciding. So this coordination skill can be replaced by a VLM or LLM in a way. So a VLM that's taking visual inputs can decide, okay, given my task of picking up the cup from the kitchen counter, right now I just need to navigate to the kitchen counter. So the VLM decides to first call the navigation skill. Once you reach the kitchen counter, it decides, okay, I'm close enough to the kitchen counter. Let me pick up the cup. It picks up the cup. Then it says, okay, now navigate to the dining table. It starts navigating. So the coordination skill is where the VLM or LLM comes in. And we do experiments that I showed where we replace the coordination skill with an LLM. The corrective skill, I would think of it as a low-level adaptation. So individual navigation, grasp, and place skills, since they are trained on individual tasks of navigation, grasping, and picking and placing, they will have out-of-distribution situations. For example, if the robot is far away from the target object, when you try and ask it to grasp, this was never in the training data set. And now something has to adapt the output of the skill to either push the base closer or stretch the arm further or essentially, call navigation again, for example, right? So the corrective skill, I would think of it as low-level adaptation to out of distribution generalization as well as a Sim2Real adaptation of it. And the LLM and VLM will play more in the coordination step. Does that answer the question? Understood correctly?
Okay, great. So we have a list of excellent questions here. Many of them is great to see the engagement. So shall we read them like each one, answer it? We have very limited.
Yeah. Oh, sure. Either is anything's fine by me. Sorry, I can't see them. Oh, there they are. Would you like me to? I don't know. What would you like to do?
So let me. It seems that there is a question on safety. And this question is about how do you handle the dynamic danger zones? For example, avoiding the crawling infants. Would you like to?
Yeah. So again, like I think danger zones in reachability clearly are not typically dynamic, makes it much harder. I would say that you could think of on the other hand, actually from learning itself, we can see that there is some amount of for example, a robustness to moving obstacles and so on, right? So this policy is not trained with safety; it's trained with the reward function of avoiding any obstacles. And when I was training it, I added like humans in the environment, right? For the Similarly here, human is a moving target and moving obstacle, and the policy is able to follow this target or avoid this obstacle when it comes towards it, right? So basically, I think reinforcement learning is able to deal with this without guarantees. On the other hand, I think, reachability has a harder time generalizing to these settings, but if I was basically dealing with dynamic danger zones, I would make them almost at least crawling infants, for example. I would make them a worst case disturbance, right? So if you can detect um, a crawling infant, this basically becomes a disturbance that you should be able to stop and avoid um, um, if you applied the best case controller. So yeah, should we move on to the next question or?
Yeah, that's perfect. So yeah, let's move on to the next question from Xu Tao. And the question is about spatial reasoning. I think that's a really nice topic to delve into a bit more. Is yeah, so given that the question is given that LLM training is token based, how do you enable it to learn about spatial relationships and meanings?
Yeah, so in this particular work, we were not actually giving, so we used this is essentially, where we used LLMs a lot in the setting was for given a text-based representation of the world, a reason about what are the actions that you need to do. And this text-based representation is basically updated at every step, but it basically is saying things like the human is in the bedroom. Um, mm, these are the objects you have seen so far in the environment, and this is where they were located. Um, this is clearly very limiting. So something that we looked into is actually adding a VLM here. So this VLM now is taking visual inputs of the environment and then breaking them down into some low dimensional tokens and then using that for reasoning. And even VLMs are not very good at spatial reasoning, right? So they're still not able to reason about this thing is next to the other thing very well from images. So what is on the left of this versus what is on the right of this is not very easily, um, it's not very robustly identified by VLMs even now. So in the future, basically, I think what we are looking, some part of my team is basically looking into is actually using kind of point cloud-based representations and then combining these point cloud-based representations with LLMs. And there have been some very interesting works on basically multimodal point cloud-based models. But I think the challenge there is like, how do you take such a high dimensional, basically, if every point in your point cloud is a token, then you can represent very in details of the environment, but like then it's almost too much information for LLMs to process well, even with long context. And of course, point clouds have the dynamic problems again right now that, if you have a moving obstacle like a human, you have to keep updating the point cloud of the human at every instant, which is also, a bit challenging. So I think basically there's a trade-off that you could use a text-based representation and then you're using like some object detector models to come up with this text-based representation, and this representation gets updated really fast. And the LLM is able to reason over this updated representation. Versus you can like use a more detailed, very detailed representation like point cloud, but now it's challenging to process this point cloud as well as updated at test time for dynamic environments.
Okay, that's great. Thanks for that clarification. Yeah, it looks like the time is up, and while we have also other questions, I would encourage you to reach out to Dr. Lai afterwards regarding this. And let's thank Akshara again for the fantastic talk, and thank you all for the engagement and thoughtful questions. Have a nice rest of your day, and hope to see you in our next Agent Frontier seminar.
Thank you so much for the invite. It was great talking to you all.
Thank you, Akshara. Take care.
Bye.